Hey everybody, this is 11J, Momentum and Energy in Collisions. It says we have two small carts, cart 1, which is mass 5 kilograms, and cart 2, which is mass 10 kilograms, are set into contact with each other at position 0 on a larger platform. The platform is centered at position 0 and is 24 meters long. So that means that from the edge to the 0 is 12 meters there. The carts in the platform can roll on bearings of negligible friction. All right, there's wheels down there. At time t equals 0, a small spring between the two carts expands, okay? Sending cart 1 to the left with an initial speed of 4 meters per second. Both carts collide and bounce off the bumpers here at the ends of the platform, which can be assumed to be perfectly elastic. When the carts collide and collide with each other again, they stick together. Okay, so a lot to unpack here. One is because the spring explodes between the two, we start off with a super elastic situation here. So we have no energy, no kinetic energy, and we have potential energy converted into kinetic there. When they collide with the walls here, we have, as they explicitly said, a perfectly elastic collision. So we get all of that energy back after the collision. And then they stick together, so that is a perfectly inelastic collision. And so that is the last thing that we do. So we know that we will lose energy in that perfectly inelastic collision there. Okay, so now that we understand all of that, let's go to the next part. And it says, for this part, assume that the brakes on the platform's wheel are set so it cannot move. All right, so now we don't have to worry about the wheels on the platform. The carts collide again at time t equals 8 seconds. So they tell that to us. All right, so do the carts collide again at, to the left of, or to the right of x equals 0? All right, so basically, do they meet here, or somewhere over here, or somewhere over here? After colliding, are the two carts moving to the left, moving right, or not moving? So a second question there. Where do they meet and how are they moving? So in a clear, coherent, paragraph length response, explain all of this. So, okay, so here's the first thing. We have no outside forces. And so what that means, since we have no outside forces, P is conserved, momentum is conserved for our system here. So no outside forces, momentum is conserved. Since 2 has 2 meters per second, so cart 1 is 5 kilograms. Let me draw here. All right, sorry, 5 kilograms, and it says it was going 4 meters per second. So we have to conserve the momentum. So cart 2 is 10 kilograms, twice the velocity, or twice the mass. So it's going to have half the velocity there. So 2 meters per second is the speed of cart 2. So the speed of 2 is 2 meters per second. So what that means then is number 1's going 4, number 2 is going 2 meters per second. So 1 will hit the wall first. And that also means because it's perfectly elastic, it will keep its speed. So it will keep its speed because it's elastic. So an elastic collision is going to come back with 2 meters per second. And so since we're going to get the wall first because we're going faster, and we're not going to lose any of our speed when we bounce off because if it's elastic, then the whole time cart 1's got a head start in a sense. It's covering more distance, so that means we're going to collide somewhere over here. So the collision will happen to the right of 0. So they will collide right of 0 there. Now, what about this question, are they moving or not? So this question has to do with that even after we collide, momentum is still conserved all the way through the problem. So we still have conservation of momentum going on. Our initial momentum was 0 before they started going. So our total is still 0 momentum, so no motion. And so we know that after they stick together, nothing can be moving at all. So just sort of think about it like this. In the beginning, nothing's moving, no momentum. Afterwards, their momenta cancel because this one's got twice the mass but half the velocity. After they stick together, we're back to not moving again. Okay, so now, next part here, let's do a graph of how the momentum of the system, two-cart system, so the momentum of the two-cart system, how the momentum changes with time and how the energy changes with time here. So we need to know when we hit this outside wall here. So number one is coming along, it hits the outside wall. That is an outside force to the system. And so it's going to cause an impulse and it's going to change the momentum of the system. Same thing when 2 hits the outside wall. It's going to change the momentum of the system. So let's figure out first when 1's going to hit the wall. We know that we've got to go 12 meters to the edge of the wall. And we know that we are going 4 meters per second. And so at 3 seconds, we are going to hit that wall. So come along here, no change, no outside forces until 3 seconds. That outside wall is going to exert a force to the right, and they say count to the right as positive here. Positive momentum is rightward. And so we're gonna get an increase in momentum. Now, how much? So let's look at that. Our change in momentum will be our mass times our change in velocity. So we have 5 kilograms, and we go from going 4 meters per second that way. We won't lose any speed because it's elastic, so we'll go 4 meters per second this way. So it's a total change of 8 meters per second in the positive direction, which means 40 kilogram meters per second of momentum. So we're gonna go up here to the 40. Now, after that, until cart 2 collides, now there's no more outside forces. So when will cart 2 collide? The wall here is going to push this one to the left, so that's going to cause a negative change in momentum. Let's find the time at which that happens. Cart 2 also has to go 12 meters, but it's only going 2 meters per second, so it's going to take 6 seconds to hit the wall there. So we're going to continue along with this momentum that we gained until we get to 6 seconds. Now, how much will the wall change the momentum of cart 2? Well, you might guess this, but it's going 10 kilograms. Let's find its change in momentum. And it changes from going 2 meters per second this way to 2 meters per second that way. So that's a total change of negative 4 meters per second, which gives you a momentum change of negative 40. So we're back down to 0 there, and that is how our momentum graph plays out. So now let's do our energy graph here and figure this out. So first off, we had spring energy, and then that became elastic potential energy. It just says energy, so it doesn't matter. So let's figure out how much kinetic energy we gain. Cart 1 has got 1/2 times 5 kilograms times 2 meters per second squared. So 2 squared is 4, half of that is 2 times 5. Sorry, it was going 4 meters per second squared, my bad, sorry. So cart 1 was going 4 meters per second squared, so 4 squared is 16, half of that is 8, 8 times 5 is 40. So we have 40 joules of energy from cart 1. Let's do cart 2, 1/2 times 10 kilograms times 2 meters per second squared. So 2 squared is 4. Half of 4 is 2, and 2 times 10 is 20 joules from cart 2. So that means altogether we had 60 joules. And that went from elastic potential to kinetic. Now, when we collide with the wall at 3 seconds, it says it's elastic, so it doesn't change the energy. And back here too, when we collide with the other wall, it's elastic, so it doesn't change the energy. Now, I really wish they'd extend this a little bit more, because right here at 8 seconds, they collide again, and we said they stopped moving. So all of that energy is now gone, and it goes out like that. Where did the energy go? Sound, heat, light, deformation of the blocks there. So, but the energy is gone. All right, last part here. It says, now suppose the platform's wheels are free to roll, but the platform has much more mass than the 2 carts. If the experiment is repeated again exactly as before, will the center of the platform be to the left, to the right, or at x equals 0 when the carts collide again and stick? Briefly explain your reasoning. Okay, so let's do before here, a little drawing. We're at x equals 0, this is the center right here, and our platform is right here. Whoops, I didn't really draw that level, and our 2 blocks are right there. So if we think about this, let's think of the 2 blocks and the platform as all one system. if we think about the two blocks and platform as a system, then there are no outside forces on this system. So there's no change in momentum. There's no movement. So no outside forces, no movement overall. And so afterwards, let's continue this line down. We know that our blocks meet and stick together somewhere to the left of this line. And so that means that our platform had to shift somewhere to, the blocks stick and meet somewhere to the right of the line. And so therefore the platform had to move somewhere to the left of that line there. So mass of blocks moves right. So mass of platform moves left.